Yo folks, welcome back to the lesson on similarity in right triangles. We're going to wrap up some of the stuff that we began in the previous video. I did say that we would be covering finding a distance, but didn't quite get there. I just stopped it at identifying similar triangles. So we will continue with that, and we're going to jump into finding the geometric mean. Now, some of what we're going to talk about today involves understanding algebra. So you might have to go back and watch some previous videos. But before we do, let's jump into some notes because things are going to get a little bit tricky. So here are the notes for the lesson. When we talk about geometric means, we've got to understand what's going on. So this note is all about the altitude of that right triangle we talked about in the previous lesson or the previous video. But we're going to talk about the altitude to the hypotenuse. So this is all about the altitude of the hypotenuse. Now, the length of the altitude to the hypotenuse is the geometric mean of the lengths of the segments. Now, what does that mean? So you have to remember when we look at this little formula here, we have AD here and then DB here, but we're talking about the altitude, which is CD. Okay, so here we have our little proportion. This is what we talked about. The relationship of AD to CD is equal to the relationship of CD to DB. Now, how is that so? Now, the reason why that is so is that if you remember our three triangles, okay, we have our large triangle, we have our medium triangle, and our small triangle. Okay, so when we talked about our three triangles, how did that work? Okay, so the large triangle, C was the hypotenuse, or the right angle, C to A was the short leg, C to B was the long leg. In the medium triangle, D was the right angle. D to C is the short leg. D to B is the long leg. And in the small triangle, D is the right angle. D to A is the short leg. D to C is the long leg. Now, taking a look at the altitude of the, or to the hypotenuse, CD. So we have CD here, okay, and CD here. So how are they related? Okay, how are they related? Well, we have a neat little relationship here. The relationship is that the ratio of AD to CD is equal to the ratio of CD to DB. Okay, we have to understand what just happened there. When we have our similar triangles, the ratio of AD to CD is equal to the ratio of CD to DB. That's what this is saying. Okay? So it's hard to just look at this picture and jump right there. We have to explain it with our similar triangles. Now that we've understood that, if you didn't understand that right there, make sure you hit pause and rewind. Okay? And make sure you see the first video. But now, what's going on here? We have to remember some things about proportions. Okay? So if you remember proportions, we have extremes. Okay, so the extremes are down here. And the means. So here we go with that word again, means and extremes. So what do we know about cross products? The cross products means the means is equal to, the product of the means is equal to the product of the extremes. So the length of the altitude, right, that CD represents the geometric mean. Okay, so the altitude of the right triangle, the altitude to the hypotenuse, is the geometric mean of the other two legs that it is proportional with. Okay, so we have to understand what that means. So once we understand what that means, we can start seeing some more things about geometric mean. Okay, so we'll take a look at geometric mean in a second. Let's do another note. It's another, what's called a corollary. Okay, so another note is very, very similar. It's the same type of thing. This is all about the altitudes. All of the altitudes represent the same relationship that we just discovered. Okay? All of the altitudes represent the same relationship that we just discovered. So again, I'll make small, medium, and large triangles, and we'll operate the same thing. So C is the right angle, C to A is the short leg, C to B is the long leg, and the medium triangle, D is the right angle, D to C is the short leg, D to B is the long leg, and then the small triangle, D is the right angle, and then D to A is the short leg, D to C is the long leg. So this is all about the altitudes of the original right triangle. In the previous note, we saw that the altitude was CD. Well, what is another altitude of the original right triangle? Another altitude is actually CA. Okay, so the other altitude is CA. Now, where else will we find CA? Over here. Okay, so we have proportional relationships with CA, or AC as this is saying. So as this points out here, that means the relationship of CA to AB, right? Because we're talking about hypotenuse. So AC to AB, if we look at AC to AB, is going to be equal to this relationship, right? It's going to be really equal to AD to AC. Ha! So don't you find that interesting that that altitude has another geometric mean relationship? Okay, so it's a geometric mean, geometric mean. So once again, this is about the altitudes. The altitudes are the geometric mean. I'll show you a trick in a second as well. So we also have another altitude of the large triangle. Another altitude of the large triangle is also BC, or CB as the book is calling it. So the other altitude is BC. So in the large triangle, the other altitude is BC. Now, where else do we find BC? We find it in the hypotenuse of the middle triangle. So if we're talking about the leg BC and the hypotenuse, well, we can set up another portion. CB is related to AB, just as DB is related to BC or CB. Okay, so it's the same thing. So here we go. Again, another equal proportion. That's what's happening here. Okay, we have the mean, the mean. So the geometric means has to do with the altitudes of the right triangle. So what does this mean? This means some pretty cool stuff, but we'll get into it in a second. But first, let me show you a shortcut. How do we understand this without going into the three triangles? Okay, so one of the ways that we can talk about it is that when we are looking at the first geometric mean, which is the altitude, okay, so this altitude was related to both AD and DB. So this altitude was related to both AD and DB. So notice how I can relate the altitude to the things I can touch. I can touch the other two legs, or the other two sides, right? I can touch the others. Okay, so that means CD is related to AD, and CD is related to DB. Okay? But since I am making geometric means, I know where my CD is going to be. So notice how that worked. Since I am talking about geometric means, I know where my CD is going to be. But what is it related to? It's related to AD and DB. Okay, so notice how we can get there with a little cheat. I can touch the others, and so I know my altitude is my mean. So does that work with the other two? As a matter of fact, it does. So let's take a look here again. Remember, this is about the altitudes. So if we talk about the altitudes in the big triangle, we talked about CD. So what are the other two legs I can touch? Okay, so if we have CB now, CB is an altitude, and since CB is an altitude, I know CB is my geometric mean, but what is it related to? It's related to the other two sides that I can touch. I can touch DB, right? And I can touch AB. Whoa. It can touch DB, and I can touch AB. Isn't that weird? So I can have my relationship here. So hopefully you saw that. It's the things that I can touch. Okay, so my altitude CB is related to the geometric means of the other two sides it is proportional with. Those are the sides that we can touch. Right? Isn't that cool? So what about the other altitude? We talked about the other altitude of CA. Right? CA is an altitude, so I can make a geometric mean. CA or AC is the book call it, doesn't matter. So I have my geometric means. So what is CA related to? The other two it can touch. CA can touch AD, and CA can touch AB. Okay, so there's my geometric means. So, cats, what are you talking about? Here's what I'm talking about, okay? So this is what I'm talking about. Let's do some examples. You'll see how this all plays out. If you didn't understand what I can touch, I'll do a couple examples. Otherwise, you got to stick with this, okay? Okay. So let's ask this question about geometric mean first. The question is, what is the geometric mean of 6 and 15? What this question is asking is this. How do I find the geometric mean of 6 and 15? This is what the question is asking. I have something here, something here. What is the geometric mean of 6 and 15? That is what this question is asking. The reason why we get there, you'll see as we use the previous note. And the other question asking here, what is the geometric mean of 4 and 18? What is that question asking? What is the geometric mean of 4 and 18? Okay, so we have to know what our geometric means are. Remember what the means are, how we locate the means versus the extremes. All right, but before we can talk about applying this example, when we talked about geometric means, we have to remember how to solve equations like this. This is going to be a little bit of a history lesson from algebra. Now remember how this works. The products of the means is equal to the products of the extremes. So we have x times x, which is x squared. That would be equal to 6 times 15, and 6 times 15 is 90. All right? So how do we solve this? Okay? How to solve. Now the way we undo an x squared, is by taking the square root of x. So that's how we undo an x squared. We take the square root. So in order to undo x squared equals 90, we have to take the square root of both sides. So we take the square root of x squared and the square root of 90. Taking the square root of x squared leaves us with x, and the square root of 90 is the square root of 90. But we must simplify our answer. So make sure you remember the video lesson on simplifying radical expressions. Okay, so the square root of 90 is the square root of 9 times 10, which is 3 root 10. So the geometric mean is 3 times the square root of 10. So we have to recall how we solve both x squared equations and how we simplify radical expressions. So a lot of history that must be done. So the other question again, what is the geometric mean of 4 and 18? So remember how we figure this out. Cross multiply, x squared would equal 4 times 18, let's see, is 72. Okay, so we take the square root of both sides. So the square root of x squared is equal to the square root of 72. So that means x equals the square root of 72. But what is the square root of 72? A few different ways to get there. Okay, square root of 72 happens to be 9 times 8. All right, so this is how I'm going to figure it out. So 72, the square root of 9 times 8, which means it's 3 root 8. But square root of 8 can also be simplified. It's 3 times the square root of 4 times 2. And the square root of 4 is 2, so that would be 6 times the square root of 2. And again, if that was too fast, please make sure you watch the previous video on simplifying radical expressions. Okay, a lot of previous material coming on here. So that's the geometric mean of 4 and 18. But what does that have to do with all of this? Okay, so remember the notes. This is just a little bit of review. So remember the notes. What do we do with that? We do this. What, in this example, are the values of x and y? How is it that we solve? Now, hopefully we notice that x and y are both altitudes of the big triangle. Okay? So we can do this one of two ways. We could use the shortcut way, or if you don't remember the shortcut, let's make 3 triangles. Okay, we're going to make 3 triangles now. Big, medium, and small. Okay, so in the big triangle, when the big triangle x is our small leg. The hypotenuse would be 16. We don't know the long leg, and that's okay. In the medium triangle, y is our small leg, 12 is the big leg. And in our small triangle, hopefully you can see this, in the small triangle, 4 is the small leg, and x is the hypotenuse. So we can do a few things with this relationship. Okay? We can set up some equations. We can solve for x and y. We can look at an example here. You know, which two triangles have x's with the hypotenuse and the short leg? We could see here that 16 to x would equal x to 4. Okay, then we can solve for x that way. And then once we do solve for x that way, we could have a relationship with y. Okay? Or, if you recall the little shortcut, x is an altitude, right? How do we find the geometric mean of an altitude? Well, the altitude is the geometric mean, so we know that x is going to be here. And what can x touch? X can touch 4, and x can touch 4 and 12. So x can touch 4, and x can touch 4 and 12. So either way you set it up, you're going to end up with the same setup. Okay, so it doesn't matter how. You can make your 3 triangles and look for proportionality that way, or you can use the cheat. Okay? So how does this work? Well, let's solve. Let's cross multiply. X squared equals 4 times 16, which is 64. So the square root of x is equal to the square root of 64. We find our value of x to be 8. Okay, so we now have figured out the value of x to be 8. And once we find the value of x to be 8, well, we have a pretty good go at it, because look, we have proportionality between here and here and there. We can do the same thing with y. Okay? But it's going to be hard to find y because we don't have a long leg other than the 12 that's given here. So without using the Pythagorean theorem, which we can, how is it we're going to figure out y? Because we don't have the hypotenuse here to compare these two. So we know x is 8. How is it that we find y? Well, once again, y is the geometric mean. Y is the geometric mean because it's an altitude. Okay, y is an altitude of the 2 lengths that it touches. Y touches 12 and y touches 4. Okay, so y touches 12 and y touches 4. We can now find the value for y. Okay, so we have y squared would equal 12 times 4 is 48. So when we take the square root of both sides, y is equal to the square root of 48. But the square root of 48 happens to be able to be simplified. Let's see, what's a quick one? I don't know, so I'll do a slow one. 4 times 12. So y equals 2 root 12, or y equals 4 root 3. There we go, 16 times 3. Should have known better. So we have now found the value of x and the value of y using the shortcut. Okay? One more example, and then we'll wrap it up, and we'll do some other stuff later. Okay? So this will be another three-part series. So here we go. What are the values of x and of y again? You can use big triangles, Pythagorean theorem if you want, or we could use small triangles. Now, we notice here that x is an altitude. Okay? So x is an altitude, so x is a geometric mean equation. What is it related to? The 2 sides it can touch, 4 and 9. Hopefully you see that. X can touch 4, x can touch 9. So x can touch 4, x can touch 9. There's our equation. X squared equals 36, so x equals 6. Not bad, right? Pretty easy. What about y? Y is an altitude as well. And if y is an altitude, it is a geometric mean. So we can set up our proportions. Oh, that's upside down. We can set up our proportion, although it would have worked, such that y is the geometric mean. Okay, so y is the geometric mean. What does it touch? Y can touch 4. Y can touch 5. Y can touch 4. Y can touch 5. Cross multiply. Y squared equals 20. Simplify. Y is equal to the square root of 20, which means y is equal to 2 times the square root of 5. And we have now found the value of x and y. Okay, and again, if this is the square root stuff is too much, you have to watch the previous video. So that's enough for now, because we get into crazier quadratic equations later. Factoring comes into play, but I'll get into that at a later time. So that'll be the next video when we wrap up this lesson on similarity in right triangles. See ya.